In the previous chapter, we saw how to calculate the efficiency of a heat engine. What are the factors that allow a heat engine to operate with maximum efficiency? A French engineer, Sadi Carnot, proposed that a heat engine has maximum efficiency when the processes within the heat engine are reversible. A reversible process is one in which both the system and its environment can be returned to exactly the states they were in before the process occurred. Therefore, a process that involves an energy dissipating mechanism, such as friction, cannot be reversible, because the energy wasted due to friction would alter the system or the environment or both. Friction is not the only reason why a process would not be reversible. For instance, the spontaneous flow of heat from hot to cold is irreversible, even though friction is not present. In fact, all spontaneous processes are irreversible. An explosion of an unstable chemical and the bursting of a balloon are examples. No automobile engine is thermodynamically reversible, since friction in the engine exists no matter which way the engine runs. The idea that efficiency of a heat engine is a maximum when the engine operates reversibly is known as Carnot's principle, which offers an alternative statement of the second law of thermodynamics. No irreversible engine, operating between two reservoirs at constant temperatures, can have greater efficiency than a reversible engine operating between the same two temperatures. Furthermore, all reversible engines operating between the same temperatures have the same efficiency. Carnot's principle is a remarkable statement. It does not matter whether the working substance is a gas, liquid, or solid. As long as the process is reversible, the efficiency of the engine will be maximum. However, Carnot's principle does not state or even imply that a reversible engine has an efficiency of 100%. It can be shown that if Carnot's principle were not valid, then heat could spontaneously flow from a cold substance to a hot substance, which would violate the second law of thermodynamics. While no real reversible engine exists, it is useful to consider an ideal reversible engine in judging the performance of real engines. The figure below shows a reversible engine, also called a Carnot engine. An important feature of a Carnot engine is that all the input heat, QH, originates from a hot reservoir at a single temperature, TH, and all rejected heat, QC, goes into a cold reservoir at a single temperature, TC. In other words, none of the input heat is lost to energy dissipating processes like friction. Carnot's principle also implies that the efficiency of a reversible engine is independent of the working substance of the engine, and therefore only depends on the temperatures of the hot and cold reservoirs. As we showed earlier, the efficiency of a heat engine is given by the following, where the ratio QC over QH can depend only on the reservoir temperatures. This observation led Lord Kelvin to propose a thermodynamic temperature scale. In other words, he proposed that the thermodynamic temperatures of the cold and hot reservoirs be defined such that their ratio, Tc over Th, is equal to the ratio of Qc over Qh, where the temperatures of the cold and hot reservoirs are expressed in kelvins. Using this result, we can write the efficiency of a Carnot engine in a very useful way. In particular, E Carnot is equal to 1 minus the ratio of Tc over Th. This relation gives the maximum possible efficiency for a heat engine operating between two Kelvin temperatures, Tc and Th. Notice that in order for the Carnot efficiency to be equal to 1, or 100% efficient, the temperature of the cold reservoir would have to be absolute 0 Kelvin. However, as we will see later in this chapter, experiments have shown that it is not possible to cool a substance to absolute 0, so that nature does not allow a 100% efficient engine to exist. As a result, there will always be heat rejected to the cold reservoir whenever a heat engine does work, even if friction or other irreversible processes are completely eliminated. The rejected heat is a form of thermal pollution. The second law of thermodynamics requires that at least some thermal pollution be generated whenever a heat engine does work. There is no way to eliminate this thermal pollution, and it can only be reduced if society reduces its dependence on heat engines to do work.